Today's focus is going to be on graphing trigonometric equations again.
What we're going to be talking about today quite a bit is the sketching of graphs, and in particular we are just talking about the sine graph. We'll just talk about y is equal to sine x, and I'll also talk about y is equal to cos x. We're not worrying about tan graphs yet, they're more complicated. These two both follow a pattern that makes it pretty easy to follow. So if I'm sketching both of these over the domain 0 to 2 pi, and I'm doing this introduction very quick because I'm assuming that most of this you should have picked up in the interactive lesson that we had last week. So that was last Tuesday where you would have been playing around with Desmos. If we're sketching this from 0 to 2 pi, I would usually draw my x and y axes. I make a nice long x-axis when I'm doing trig functions, x and y. I am going from 0 to 2 pi, so I'll label my, oops, I didn't mean to change the color then. So I'll label my 2 pi there and then just estimate roughly that's about halfway there. So I'll call that 1 pi. That's about halfway there. So I'll call that pi on 2. That's about halfway there. So I'll call that 3 pi on 2. I like to also put a little, indicate where my maximum is. And in this case, we should remember that my maximum is at 1 and my minimum is at -1. So I draw those little dotted lines there. That's the sort of habit you get into for sketching every single graph that you're going to be doing. And then our sine graph starts at 0, goes up to a maximum pi on 2. Do your best to get a nice smooth curve. I'll try that one again because I stopped halfway. A nice smooth curve that comes down through pi, touches the minimum there and goes back up. So that's our sine graph. Our cos graph, I'm going to do this very quickly. I won't label everything. But the most important thing is that our cos graph is very similar, apart from the fact that it starts at 1. And we should remember that because in our unit circle, we know that cos is a distance away from the x-axis. And so if we're starting at an angle of 0, our distance distance away from the y-axis, the length of this line here starts at 1. And as we go around the circle, it gets to 0 and then gets to -1 and then back to 0 and then back to 1. So that gives us a cos graph that looks more like this. So they're actually the same shape. This is really just a translation. If I take this sine graph and cut it off there and take this bit of it that I in that first quadrant and stuck it on there, we get exactly the same thing. These two graphs are exactly the same shape. And that makes life a lot easier. That means that we're pretty much dealing with them at exactly the same time. All right, now that's great for the nice simple ones, but almost definitely you're going to have to deal with transformations, and transformations really work exactly the same way as they did in the functions unit. And what I mean by that is if we've got something like y is equal to a sine, hang on, let me give you an actual value, y is equal to 2 sine x, then it's just going to look the same as the previous graph, except that we've dilated it by a factor of 2. And that's going to mean that instead of a maximum of 1, we're going to now have a maximum of 2 and a minimum of -2, and that's the only change there if we're sketching 2 sine x. What we might also do, what happens if we have something like 2 sine x plus 1? Well, in that case, yeah, we know that we're going to go, our graph is again going to be basically the same, except we've shifted it, we've translated it up. We're going to deal with those sorts of questions more tomorrow's lesson. I'm not worrying about vertical translations in today's lesson. What I will be worrying about is horizontal translations and horizontal dilations and how they affect it. But before we go any further, let's define a couple of words that you should have seen before in our interactive lesson. And those words are really common across sine and cos. We're going to be dealing with what is the period of our graph and what is the amplitude of our graph. Working these things out from the equation makes sketching it a lot easier. Now, our default value for the period is 2 pi, because by definition, our period is the time that it takes, or rather the x value distance, the domain over which it takes for one cycle of our graph. And so in this case, we're starting at 0, we go up, we go down, we get back to 0 there, that's one cycle, and that's 2 pi. Essentially, it's also asking us how far it takes to go round the circle, which is 2 pi in our basic situation. but it won't always be. Our amplitude is defined as the distance from the mean point, 0, to the maximum point, which is also the same as the mean point, 0, to the minimum point. But in this case, in our basic case, our amplitude is 1. Now, if we've got our general trig equation, something that looks like y is equal to a sine of n lots of x plus b, sorry, that should be a minus b, but it doesn't really matter, minus b plus c. This is our general form of our trig equation. What's our period and amplitude now? Well, our amplitude, oh no, I wrote them as period before, so I'll call it period now. What's our period? Our period is always defined as 2 pi divided by the value of n. Let's think about why that might be. If I'm sketching y is equal to cos 2x, this 2, based on our knowledge from function study, this 2 here gives us a dilation, a compression. So it's a dilation of factor of a half in the direction of the y-axis. Sorry, direction of the x-axis. So I'll draw it in red up here on my cos. If we're doing a dilation of factor 2, we're essentially fitting in 2 lots of our period in the time that we previously took 1. So this blue line here is y is equal to cos x. This red line here is y is equal to cos 2x. And they're identical apart from the fact that we've done that horizontal dilation by a factor of a half. And so the effect of that, what's been the effect of that on the period? Well, we've obviously halved our period. So we're dividing, our base period is 2 pi, and we're dividing that by 2 to get our new period. And so our period is always 2 pi over n, which is really handy to remember. Let's also remember this relationship's going to go both ways. So it's also really handy to remember that n is equal to 2 pi over the period. Because there'll be times where you're told what the period is, and you have to then go to n. So we can use that, that relationship there. What's our amplitude? Our amplitude is basically, well, our default maximum and minimums are 1 and -1. And so if we multiply our function by 2, for example, y is equal to 2 cos x, then that's going to make our function go up there. Oh, sorry, and all the way down there. And our amplitude, this distance that I talked about here between our middle and our maximum, has doubled. And so our amplitude is just quite simply whatever our a value is. As in our general form, that's what we're multiplying there. Now, there's only one little trick to that as well, which is that the amplitude is never given as a negative number. It doesn't make sense to have a negative amplitude. So if you've got a question like y is equal to -2 sine x, and a question states, what's the amplitude? The answer is 2, not -2. It's always just the absolute value. So I'm going to use these absolute value symbols around my a to say that we just always give our amplitude as a positive value. So anytime I'm sketching a trig function, like when I'm sketching a normal function or a quadratic function or something else, I have my key points. I like to say, what's my shape? What's my y-intercept? What's my x-intercepts? What's the turning point if it's got one? What are the key points? And I just try and label those explicitly and show working out for those. It's exactly the same if we're doing a trig function, but we've also got period and amplitude as the 2 extra things that we want to do. So I'm going to sketch a graph. I'm going to go through an example. Today's lesson is really going to be me giving you 2 examples of sketching sort of complex ones. We're going to jump straight in. You should have already done some sketching in our on Tuesday's lesson, but now it's going to get a bit more complex. So I'm going to go through 2 examples, and then the rest of today's lesson is you just practicing sketching things like that. All right, so let's have a look at the first one I'm going to sketch is y is equal to sine x minus pi on 3 over the domain 0 to 2 pi. So when I'm doing this, I like to state a few things. First of all, we can very easily find out what our y-intercept is. We can do a few different things in different order. Shape makes sense. It's a sine graph, so I sort of just draw that for my sine. If it was a cos graph, I'd just sort of do that. Anything that just shows that you're starting in the middle and going up. My y-intercept is going to be when x equals 0. And so in this case, that's y is equal to sine of negative pi on 3. You remember that we did lots of problems like this, and I described them as the sort of bread and butter of this sort of unit, and that's why, because we're going to need to solve lots of those sorts of problems in a situation like this. And so we know that sine is, we're negative pi on 3, which is down there, and thus sine is going to be negative because we're below the line, and the base angle for pi on, that gives us sine of, and the answer for sine of pi on 3 is root 3 on 2. So thus our y-intercept is equal to negative root 3 on 2. That's the sort of amount of working that we expect to show for that. All right. Let's also talk about our x-intercepts. Actually, I won't do that just yet. One really important thing is to state maximums, where the maximum point occurs. Well, there will be several, or there may be several, I should say, in a defined period. To do that, it's really easy if we have defined our period and our amplitude before. So somewhere in your working out, you should state what's our period. And in this case, our period, there's no n value. We're not multiplying this x here by anything. Remember, if there was either a value inside the brackets like that, then we'd have to worry about it, or if there was a value outside the brackets like sine 2, lots of x, either of those give us an n value of 2. But in this case, there isn't any of those, so our period is going to be 2 pi, and our amplitude is going to be equal to 1. Stating those right at the beginning makes life really clear. All right. Finding the maximum is really useful, or just finding out where a maximum occurs. And the way that I like to do this, there's a few different methods, but the way that I like to do this is to recognize, okay, we're dealing with a sine curve. Whereabouts is sine maximum? Sine is maximum at that value there, which is a theta value or an x value of pi on 2. Sorry, I shouldn't say an x value. I'll call it a theta value because I don't want to get confused with the x that we've got. Okay, so a sine graph has a maximum when the angle that we're finding the sine of is pi on 2. Now, in this case, this is the angle that we're finding the sine of. So I like to state that the maximum occurs when that thing inside the brackets is equal to pi on 2. So I'm going to say the maximum occurs at pi on 2 is equal to x minus pi on 3. All right, so all I've really done is taken the bit inside the bracket. If we were dealing with a more complex example, for example, if you were doing something like finding cos 2 lots of x minus pi on 4, then, no, I won't make it complex with a cos because I'm dealing with sine at the moment. Let's just say that that's a sine. Say we're dealing with this function and you want to know where the maximum is. Well, you know that a sine function has a max at pi on 2. So we're just going to set pi on 2 to be equal to the thing inside the sine function bracket. So 2 lots of x minus pi on 4. And then you do some algebra to solve that. So in this case, you'd have to halve both sides and then add pi on 4 and you'd get your answer, which I'm not going to worry about now. All right. But in this case, our solving for algebra is to add pi on 3 to pi on 2. The common denominator is 6. And so we've got 3 pi on 6 plus 2 pi on 6. That gives us 5 pi on 6. That's where a maximum occurs. If we were sketching for over more than 0 to 2 pi, this thing here, 0 to 2 pi, is one period of the graph. So we know by definition we're only going to get one maximum in one period of the graph, or possibly two if they're right on the edge. But if you wanted to know where other maxima are, the really easy thing to do is, once you've found one of the maxima, like that way, that's where one maximum is, the others are just a period away. By definition, they always need to be a period away. So since our period is 2 pi, we could, if we wanted to, state where other maxima are by just adding 2 pi to that. 2 pi is the same as 12 pi on 6. So we're also going to have a maxima at 17 pi on 6 and at 29 pi on 6. And we can just keep on going. Obviously, we're going to get maxima in a lot of different places along the way. All right. Now, where does our minimum occur? If you've worked out where 2 maxima are, so don't worry about that one for now, then the minimum by definition must be halfway between the 2 maxima. So in this case, what's halfway between 5 pi on 6 and 17 pi on 6? Well, that was a difference of 12 pi on 6. So 6 pi on 6 tells me that my minimum is going to be at x equals 11 pi on 6. All right. Now, x-intercepts are going to be sometimes quite tricky. In this example, not so much. And in the examples that we're doing, in all of your exercises that you're doing today, they're not going to be too tricky because of one really simple fact. Let's go back up and have a look at our basic sine graph here. We know where our maximum is and where our minimum is. And if there's no vertical translation, if this hasn't shifted up or down, then by definition, our x-intercept must be halfway between our maximum and our minimum. We can make that assumption if there's no plus c value. So if there's a c value, we can't make that assumption. And in that case, we're going to have to use some more trickier solving equations like we did in the last lesson. The last lesson was about solving equations. That's where we're going to have to use some of those skills. However, anytime you can identify that since c is 0, we know that I'll switch back to black. We know that our x-intercept is halfway between our minimum and our maximum, which we've already identified. There's our minimum, sorry, there's our maximum, there's our minimum. And so what's halfway between those two? Between 5 and 11 is going to be adding another 3 pi on 6. So that's going to give us 8 pi on 6, which is also simplifies down to 4 pi on 3. And also halfway between our, essentially we can then add half the period, because we're also going to, if we think about what's the difference between this x-intercept and that x-intercept, it's going to be half our period. Or if you look at even the Cos graph, any of these graphs, the difference between our x-intercepts is halfway between our period. That's only when there's a c value of 0. We can't make that assumption if there's a translation up or down, but we're not going to be looking at those today. That's going to be tomorrow's lesson, is looking at when we've got a translation up or down. So in this case, my x-intercepts are going to be at 4 pi on 3 and also at 4 pi on 3 plus half our period. So 4 pi on 3 plus pi. Whoops, I wrote a 3 there. 4 pi on 3 plus pi, which gives us 7 pi on 3. All right, so we've got enough information to sketch it now. There's a lot of stuff going on there. If I was doing it on a whiteboard, you'd be able to see it all at once, or at least on a piece of paper. So let's sketch it out. In this case, some nice long axes to start with. I'm going to just put 2 pi, pi there. I pretty much always label these points, the quarter point, the half point, the 3/4 point, and the full period. Sorry, not the period. What I'm saying is I always do this even when the period's not 2 pi, or even when the end value might be different, or the shape phase shift might be different. These points might not be, sorry. Going back to our sine graph, it's clear that pi on 2 and pi and 3 pi on 2 and 2 pi are really important points, because one of them's the maximum, one of them's the x-intercept, one of them's the minimum, the other one's back to the x-intercept where it's full period. I like to label those points even if those aren't the key points. It's clear that here our maximum and our minimums and our x-intercepts aren't pi on 2 or pi or 3 pi on 2, 2 pi, but I still like to label them as such anyway, label those points. All right, so I'll put a dotted line here and we'll call that 1, and I'll put a dotted line here and I'll call that -1. Just try and get those as horizontal as you can. The worst thing to see is someone who draws their maximum looking or minimum looking something like that as a dotted line. If they're not horizontal, it can cause problems. All right, now let's just label the points that we've discussed. Our y-intercept is -√3 on 2, which is a little bit more than a half. So that's pretty close to sort of 3/4. So I'm going to put that down here somewhere. And then our shape, let's think about our shape. Here's our basic shape, which starts at 0. The question sort of is, we could go up from there, or we could go down from there. Let's work out what our basic shape is and where we've translated it. And so this is our standard basic shape, but we've translated it pi on 3 units to the right. So that means that our point that was here has now gone pi on 3 units to the right and will be there somewhere. Thus, we're going to need to go upwards from there. We've already worked out that our x-intercept was at 4 pi on 3. Well, sorry, for x-intercept is at 4 pi on 3, which is going to be there. So that's pi plus another third of pi. Sorry, it's not going to be there. It's going to be there. And 7 pi on 3, which is more than 2 pi. So that one's off here. We're not actually going to worry about that. What I should have identified is, since each of our periods is each of our x-intercepts is half a period away, we are also going to get one at 4 pi on 3 minus pi. We're going to get an x-intercept at pi on 3. So that should be enough information to now identify it. That's my x-intercept. Going a little bit further, a third of the way to the next one is going to be my maximum. Going a third of the way to the next one is going to be my next intercept. Oh yeah, it's not a third of the way. Oops, sorry. The reason being, pi on 3 is there 2/3 of the way between that point and that point. If it was pi on 6, it'd be a third of the way. We're dealing with thirds nearly all the time, unless you've got a pi on 4, in which case you're dealing with quarters the whole time. But so 2/3 of the way to there, 2/3 of the way to there, 2/3 of the way to there, 2/3 of the way to there. That first one's my x-intercept, the second one's my maximum, the third one's my x-intercept, fourth one's my minimum. And so getting a curve that tries to go through those points is going to look like that. Anytime our domain is the period, in this case, our domain is over the domain of 2 pi, and our period is also 2 pi, we're going to be finishing the same place. That it also occurs if your domain is a multiple of the period. So, for example, if you're doing 2 periods in your domain or 3 periods in the domain, you're going to finish at the same point. So this point here we identified as negative root 3 on 2. That means that this point here is also 2 pi, comma, negative root 3 on 2. We like to label our other points as well. So this minimum here, we identified our minimum is going to occur at 11 pi on 6. That's good because that's pretty close to our 2 pi. So that's where we'd expect it. And our minimum value is -1. And our maximum value here occurs, we worked out where our maximum occurs here, which occurs at 5 pi on 6. So that value there is 5 pi on 6, comma 1. And we also like to label our intercepts as well. So this thing here I'm also going to label as pi on 3. And this one here I'm going to label as 4 pi on 3. And I'm done. It's a lot of stuff there, but you are going to get reasonably good at it the more you do it. That took me a little bit longer than I wanted, but I still want to get through one more example that just highlights a couple of other things. I'll try and do this one quicker. All right, so the next question that I also want to do an example of, let's also sketch the graph of y is equal to cos. And so we'll do a Cos Graph example and you'll see how it's different. And we'll also have an n value here. So let's talk about 2 lots of x minus pi on 4. All right, so first of all, what's our shape? Well, it's a Cos Graph, so we're going to look something like that. What's our y-intercept? Y-intercept occurs when x is equal to 0. And so when x is equal to 0, y is equal to cos of 2 times 0 take pi on 4, which is 2 times negative pi on 4, which is equal to cos of negative pi on 2. What is negative pi on 2? Well, negative pi on 2 means we've gone down there and we've got a cos value of 0 at that point. So that's equal to 0. What's our period? Period is equal to 2 pi on n, which in this case n is 2. So our period is equal to pi. And our amplitude is equal to, there's no a value in this case, so our amplitude is 1. Where are our x-intercepts? Well, this one actually is already a little bit easier because we found one of them already. So since we know that we have an x-intercept at 0, by definition, because we have a y-intercept at 0, and that also means that, remember, we've got an x-intercept every pi on 2 after, or every period on 2 after that. So we're also going to have it at pi on 2 and at pi and on 3 pi on 2 and on 2 pi. And then we've got to our destination, got to our, at the end of our, sorry, I didn't put in my domain here, but we are sketching it over 0 to 2 pi. Oh no, actually, sorry, in the example that I wanted to do, let me change that. Let's not sketch it over 0 to 2 pi just because that's a little bit boring. We've done that already. Let's sketch it over negative pi to pi, which is still 2 pi in distance, but we'll see how that impacts other things that are going on. So that makes some of this information a little bit incorrect, because now we're also going to have it at negative pi on 2 and at negative pi. So that's pretty much enough information to sketch our graph. Rather than going all the way along there this time, there's not much point doing that if I'm going between if I'm going between negative pi and pi. So in this case, I'm going to have a long x-axis that looks like that. Labeling my key points, I'm only going to pi this time, and that one there is pi on 2. That's 0. That's negative pi on 2, and that's negative pi. I put in my, I'll just rub out some of that information just so it doesn't take up quite as much space. I'll put in my maximum value at 1 and my minimum value at -1. Label X and Y axes. All right, so now let's think about what we know is that we've got an x-intercept and a y-intercept there at 0. We've also got an x-intercept and a y-intercept at, sorry, and here we've also got an x-intercept at pi on 2 and at pi and pi on 2, pi. So there's sort of two different possibilities. We could either be going up and down, or we could be going down and up, and we have to think about which one it might be. To do that, let's think about what our graph is and which way we've translated. And normal Cos graph starts at the top here. That's where I'm looking. My normal Cos graph starts at the top there, but this has been a translation of pi on 4 units to the right. So that's gone to there. That means that's going to be our maximum. So sketching, we're just going to put in a curve that looks like that. Once again, I'll say it's usually a little bit easier when with a pen. Doing it on an iPad where there's no friction on the device makes it a little bit harder, but that's the smoothest curve that I can get. If you can't get smooth curves, like some people really worry or really do need to practice their curves, but get into the habit. If you start sketching it and you don't get very smooth curves, do some practice by just do that a whole bunch on a page. Fill up a whole page of just trying to get a reasonably smooth curve. That one wasn't so great because it's much steeper here than it is there. But just practice doing that hand motion a lot, and you'll get there. Anyway, that's our Cos graph. All we really need to do is label any key points. So we've got our maximum here, which is going to be at pi on 4, 1, and our minimum here, which is at 3 pi on 2, -1. We like to label our end point explicitly, even though it's a 0 and it's sort of labeled, but in this case, I'm going to say pi, 0, and this endpoint here, pi, -pi, 0. So we label our endpoints explicitly. We also have to label that negative pi on 2, negative pi on 4, -1. And this one here is negative 3 pi on 4, 1. That was an awful close bracket. That's not much better. But that's our graph. That's what we've done. So the key points, the things you really need to take away from this are, first of all, know the difference between the sine graph and the cos graph. The shape is the same. It's basically where they start. And know that when you're sketching a function like this, it's really important to state the period and the amplitude explicitly, because that makes it easy to work out where our x-intercepts and y-intercepts are. Well, rather, when you've worked out one of them, it's easier to work out where for the x-intercept, when you've worked out one of them, it's easier to work out where the rest of them are. So stating those things is really useful.